What is the speed of the ball at the bottom of the hill? We're going to use energy methods to solve. So far, we're only aware of two energies that we have, kinetic energy and potential energy. And basically what we're doing, as the ball changes height, it trades its gravitational potential energy for kinetic energy. So at the top, up here, if I look at the top of this, I'm going to look at the total energy, which is kinetic plus potential. And then at the bottom, I'm going to look at kinetic plus potential. So why am I looking at these two locations? Well, the question says, what is the speed of the ball at the bottom of the hill? So that's going to have to be down here. So that tells me I got to look at the energies at that location. Now I got to compare this to a second location. In the second location, I need to know the speed, that's going to be the kinetic energy, and I need to know the height, that's going to be the potential energy. So at the top, I know the speed and I know the height. So because I know those things, that's why I chose those locations. So that's important when you're doing this. One location is going to be about the question. The second location is going to be somewhere else in the diagram where you know the speed and the height at the same spot. Okay, so let's set this up. Let's switch colors. So I'm going to use conservation of energy. So I'm going to say sum of the energy, and it'll be descriptive. Top equals sum of the energy. Looks like a G, but it's supposed to be an E. At the bottom. All right, at the top, I'm comparing two energies, kinetic and potential. The sum of them equals the kinetic and potential. Looks like the same on both sides, but it's not. Everything on the left side has variables from the top. Everything on the right side is going to have variables from the bottom. Then I go through. Kinetic energy is all about velocity. So at the top of the hill, I'm going to ask myself, is it moving? If the answer is yes, I'll keep kinetic energy. If it's no, I'm going to get rid of it. In this case, the velocity is 0, so that's going to go away. Is it above the other location? Because it's about h for potential energy, and 3 meters is above the other location, so I'm going to keep the PE. On the bottom of the hill, I ask the same two questions. At the bottom of the hill, do I think it's moving? Yes. Usually when I fall down the hill, I pick up speed, so I move at the bottom. Is the bottom of the hill higher than the other location, which is the top? And no, it's not. So that's going to go away. So that means potential energy equals kinetic energy. So in this problem, mgh is equal to 1/2 mv squared. Well, there's an m on both sides. Doesn't always happen, but it's nice when it does. So they go away. So gh equals 1/2 v squared. And I'm trying to find the speed, so I'll isolate v. Multiply both sides by 2 to gh. And then square root both sides. So v is equal to the square root of 2gh. And then I'll put in numbers and units. So v is equal to square root of 2 times 9.8 meters per second squared. Notice there's no negative sign on the 9.8. It's just the magnitude of it. With energy, it doesn't have direction. It's one of the nice things about energy. The sad part is, because we aren't dealing with direction, we also can't find time. And then I have the height. So the height is 3 meters. So the velocity is, if I do the calculation, it's 7.67 meters per second. And notice there's nothing here about direction. It's not negative. It's not positive. It's just 7.67. So that's why I asked about the speed, not the velocity. Even though the equation has a v in it for velocity, it's really the speed that we're after.